everybody. This is the Alex Manassa, and I'm going to make a special project here pretty soon. You're going to find out what it is in a little bit, but it's going to require RGB LEDs, and they're going to need to be really, really, really bright, okay? Like bright enough to see in the daylight. We're going to do a little POV thing. That's persistence of vision. That's when you blink lights as something moves, as something moves by, and it spells out a little message because, you can change the way that these lights blink, okay? So, we got to shop for LEDs. That's the first thing we're going to have to do. Okay? So here I am on DigiKey. Okay, let's check this out. Alright, so on DigiKey, the LEDs are down in the optoelectronics. Okay? So here's optoelectronics. You got all kinds of LEDs here. Lots of them. I could spend hours and hours just explaining what all the different categories here are on DigiKey. But it's probably better if you really, really, really want to know. You might want to just go down there and see for yourself. You can click on any of these and see what kind of LEDs they're talking about, what kind of lamps there are. There's cold cathode fluorescence, CFLs, right? But we're going to talk about LED lighting, right? Because that's going to be bright enough to see in the daylight. And we're going to talk about color, okay? I could go for white, and you can get the different shades of white, the temperatures of white, warm to daylight. But we're going to do color, okay? All right, so now that we're in color, I always like to expand my filters, see what my choices are, right? So these are all the different filters of the different LEDs that are offered, okay? DigiKey is a massive warehouse. I think it's in North Dakota or Minnesota or something. It's northern Midwest, and you get to see all the different things here, right? I'm going to explain this really quick. You got your manufacturers, American Bright, all the way down to... with electronic. Then you got packaging. That's the actual package that the stuff is going to come in, whether it's cut tape, reel, comes in a circular reel. That's good for pick and place machines. Series, I never really look at. Once you like cut it down to the manufacturer, then I'll look at it. This is really important. You want it to be active. You don't want to be discontinued last time, not for new designs, obsolete, because then you'll never be able to buy it again, right? Okay, so, and the other important checkbox is in stock. You can't buy anything that's not in stock, right? So I already clicked active though, so that kind of makes things a little easier. Because if it's active, it's probably in stock. All right, next thing I want to check here is color. Color, what happened to color? What happened to color? Did color just go away? Oh no, it's over here. We may have over-filtered because I only see amber, blue, green, and red. That's not going to do it. So let's go back to... Oh, I accidentally clicked manufacturer. My goodness. All right, I didn't actually want to go with Worth. All right, so Worth. Sorry, Worth. All right, where's color? Where's color? There we go. Here we go. I want RGB LEDs because I want to be able to make all kinds of shades here. I also don't want to buy multiple LEDs. I could, for this design, I could have reds and then whites that are not RGBs, but I would like to be able to reuse this and do it and play with it. I might do a lot more with this design, so I don't like to limit myself. We want to do full RGB. If it's RGB plus, like it has these other ones, lime, it has lime. Lime's a color. Amber, cyan, and lime. All right, I just want to see what this part is. All right, amber, cyan, and lime. Oh my goodness, that's pretty cool. That's pretty cool. So you see all the different colors on there. What all it is, it's got red, green. It says two reds. Right. Okay, so it's got... What's going on here? All right, let's take a look at the wavelengths maybe. So 623 nanometers, that's red. 520, that's green. That's a shade of green. 450, that's solid blue. 590, that's amber. I'll take your word for it. I don't know. And then cyan. I don't see any lime on here. I don't see any lime. I see green. Someone might have made a mistake here. But still, that's pretty cool. That's a lot of stuff in there. Now, usually when they have these RGB LEDs, they'll have some other color. Usually it's just white to kind of amplify it, to just increase the brightness, because white spreads across all the spectrums. So it's a good enhancer. It's not always good in every situation, but if you, let's say you want to have a tunable light that is here, let me get rid of this color. There we go. Get rid of the color filter. If you want to have a tunable light that's like warm white to cold light, like surgery lights, daylight, you can just put something that's kind of middle in the road and make it really cheap, right? And pump lots of power into it, and then take the tunable part can be really not so bright, and you don't need a lot of power in it, which means it can be cheap. So the tunable part, you got a balance between tunable versus bright, right? So you put a non-tunable super bright to get the lumens up, and you got a tunable to kind of dose it one way or the other. All right. Okay, let's get serious here. So we want to get color. We want RGBs. Anything that's got RGB plus is fine. The rest of this stuff is pretty static. I don't want to do a 3 LED solution to get my pixels, because you could do 3 LEDs to get a single pixel of RGB. But I'd rather just have it all in one package. I'll pay the premium. It doesn't matter. I counted the number I need on this sort of rod where I'm going to put this persistence of vision thing. I'm going to need about 25 vertical pixels, right? The horizontal pixels are going to be determined by the accelerometer and how fast I can respond and do the integration, right? Because if I'm going to the side with this persistence of vision, right, I just need to do a double integral between acceleration to velocity to position, right? And then I can parse out my position from there. So that's more processor and accelerometer dependent. All right, so I need 25 vertical pixels, so I'll need 25 of these guys, and I'm just going to sort by price. Oh, wait, let me go ahead and apply filters, right? So you see those minimum quantities? Some of them were minimum quantity of 500. That doesn't help me. I don't want to buy 500 LEDs. I mean, I'm not that hard up for LEDs right now. All right, cool. So as you can see, I've already done the search, right? Because I don't want to meander around DigiKey forever, wasting all of your time. And I found this guy here. This is from Seoul Semiconductor. Could be a Seoul sister. Get this guy. Data sheet's right here. The lumens are pretty good. I mean, I comparatively, right? There are some on here that are like ludicrously high lumens. Actually, the easiest place to see a comparison of what you're looking at is to go up to the filters. And let's just take a look at red. All right, so 35 lumens per watt red. Right, okay. So that doesn't tell us total lumens, though. Is there something that gives us total lumens? That'd be nice to know. There we go. Okay. Luminous flux at color at current/temperature. Well, I don't know what the current/temperature that is. But, I mean, just doing a cursory look, it looks like low to mid hundreds is kind of where it's at for red. Green's kind of all over the place, actually. And that makes sense. Our eyes are tuned to see green in more fidelity. So if you want to get more bang for your buck, I suppose you'd give green the highest range. I guess. Lumens per watt test. I don't have all day to test through all of these, right? I'm going to grab the top one and just see wait, why is it? Okay. All right. Let's take a look. I just want to take the top one just as a comparison. Oof, that's a price hit. I think, yeah, I'm gonna have to test this, right? So I could do some calculations about signal to noise ratio out in the daylight, right? The daylight that's going to be around me is going to be the noise. That's the signal that you don't want. Any signal that you don't want is noise. And the signal I do want is the lumens coming from this LED. And I could find out what the right signal to noise ratio that our eyes could perceive, right? I could do that calculation and then do the calculation of lumens of the outdoors versus the lumens of these lights. But I'd rather just test it. I don't know. I could do some research. I probably will before I hit the shopping cart send button. Now that I say it, it doesn't sound like the hardest calculation. But let's pretend I'm buying this one, okay? Start the data sheet here. Here's a picture of the actual unit. I can get you a better picture. Oh, it doesn't have one. Okay. Let me see if I can zoom in. There we go. Look at that. That's pretty cool. And if you want to see the pinout, I'll just skip ahead. There we go. So you see you got your green plus, green minus, blue plus, blue minus, red plus, red minus, white plus, white minus. Just like a LED that you'd stick into a breadboard or put onto a circuit. It's just pluses and minus terminals, cathodes and anodes of these LEDs. It's really simple, actually. You can just physically see it. Here's a strip right here. It goes into one side of the LED here by these two little leads. Then that goes to probably the backplane of this LED semiconductor, which then connects to this plane here. And all of this extra copper is probably just for heat sinking, is what I'd guess. And to give it a solid anchoring to the chip itself, right? You know, what's weird here, though, is that I don't see the leads popping up over the side. Usually you see them kind of pop up underneath, and you can see it on the side here, but I don't see them on the side. That might make it pretty tricky to solder. Let me take a look here. Is there a mechanical drawing? That's an interesting layout. What is this? This is okay. All right, so it wants a solder pad. This is almost certainly just for heat sinking purposes. So when I design the footprint for this, I'm going to definitely put a lot of drill via holes to go to the other side of the circuit board. First off, because via holes are really easy to solder to, because I can't stick my soldering iron underneath of a package, right? I might have some hope on these edges, but underneath the package, I need to get some heat to it. So if I use a via, I can flood solder in from the other side of the circuit board and actually fill that out. Okay. I could just get lazy and buy a strip LED, but that's not why you guys come here, is it? We're going to do some real design. I like to make all my circuit boards myself. I mean, if I could buy a solution, I will buy a solution, and I will consider it. I probably will buy like an Adafruit RGB LED strip, but she uses the exact same one. And if she has an RGB LED strip that's built for lighting, I'll take it, but I doubt that they have anything that's even close. They're probably all indicator level LEDs, and that's just no good. All right, so here we go. Typical lumens is 122, 216, 300 lumens for the white. For some reason, blue is always in radiant power. I don't know if that's a marketing thing, because that's how they can get the bigger number. It wouldn't surprise me. Ah, man, the lumens number is so low. It's only like in the 60s. But put radiant power instead. Let the engineers do the math. No thank you. No thank you. Ugh. All right. These are just peak wavelengths. All right, so this is the peak wavelength. These are the dominant wavelengths. So this is just the spectrum. And I'll show you in a graph. They actually have a graph here of the luminous intensity of the color spectrum. Or sorry, relative spectral power distribution. Sorry about that. I got to get my optics terms right. Here's the white, right? You see the white is... I thought at first it was kind of the addition of everything, but I don't know what's going on here, why it doesn't peak out quite as much. I mean, it's obviously not the addition. I mean, it follows blue perfectly, and then it just peters out for some reason. I don't know if it's taking into account, you know, the human eye model, which I don't know why they would do that for the white, but not the other ones then. I don't know. There's a lot I don't know. I just try to figure stuff out as I go. But you can see here blue peaks out around 450. You see that green is about 520. I don't know, 520. That's its peak. And then you got your red over here that peaks around 630, probably. Okay. But you're going to see a full width half maximum. What that means is you go to the very maximum here, right? And at the halfway mark, this is all normalized. Normalized means it's been made to be 1. So this is not this is relative, right? This is not what the actual power coming out is. Oh, that might explain it. Okay, that probably explains why. Okay, this is this shape, right? Because this is not the actual power coming out. This has been normalized so that the peak is always 1. So you can just get a feel for the shape. All right, that makes sense. So at 0.5, that's the half maximum. The full width of the half maximum is how much that is spread, right? These are probably something approximating a Gaussian distribution. That's Gauss Gaussian distribution. That's just a mathematical model to show the distribution of something that's random. The emissions, the wavelength of the photon that's emitted is kind of random. It's randomized within an envelope. So you need a distribution to show. And, you know, if you took just like if you took a whole bunch of random kids from a class, gave them a test, there'd be kind of a random distribution of scores on that test. It's kind of like if you put electricity through an LED, you're going to get a random distribution of nanometer wavelengths of each photon. That's kind of how that works. Don't know what that is. I could look that up if I felt like it. I probably will later, off camera. There's the full width half maximum I was telling you about. That is in delta. Lambda is the symbol for wavelength, right? So it's just saying that there's a 19, and then green is 36, so it's spread about almost twice as much as red, and then blue is about 20, which is the same spread as red. So it just gives you an idea of how true they are to the individual color. All right, this is important. This is the forward voltage. This is the voltage drop that you're going to see at the LED, right? So just like if you made a simple resistor LED circuit, you're going to have, you're going to have a voltage drop across the LED there. This is going to be the voltage drop across. Okay, so that means that the power supply is going to have to supply at least 4.2, right? That's the main takeaway. You're going to give out at least 4.2 and then maintain whatever current. It looks like 1 amp is what this thing is built for, but we'll find out. Viewing angle is kind of important. I mean, 120 degrees is decent. That's just how head-on you can see it. Like if you go look at your monitor right now and then you go to the side, the more to the side, the more of an angle you have to your monitor, the less bright the monitor is. That's all this is saying. I wonder if they're going to give us a graph of the viewing angle versus intensity. I'm not sure. Oh, the Zener diode is included. What? Really? Oh, okay. Well, shoot. All right. I was wondering why this was so high. I mean, this is pretty high. It's like, why do you need 4.2? But they included a Zener diode in there. All right. Whatever. You see the resistor of whatever this is. Theta JS. Theta JS. What is Theta JS? You guys talking mess. Oh, okay. That's also in the same... All right. Well, I don't know what Theta JS is, so... Okay. Oh, thermal resistance. Okay. Resistance from junction to... from J to S. I'm sure I'll feel really stupid as soon as someone tells me what that is, but that's Kelvin per watt. That must be the... Yeah, okay. So that's for every watt that you put through this thing, that's how much temperature I guess it's going to rise. So if I put like a few watts, it's going to raise a Kelvin. That doesn't seem like a big deal. If I'm interpreting that right. Okay. We've already looked at that. Forward voltage versus forward current. Yes, forward voltage is definitely not uniform. So this gives us a little feel here. So it's going to be a little bit above 2.5, but yeah. Oh, okay. So it's not going to be 4.2. Oh, great. That's good. Okay. So if as long as we keep it, as long as our LED current, so we want to drive, if you want constant brightness, right? What happens inside of an LED is electrons go through, they elevate in energy level, according to the semiconductor. That's what semiconductors kind of do, is they're like a pothole energy-wise, or they're like a cliff energy-wise. Like you think of it like that. So electrons coming through, hits the hole. What happens whenever you lower the energy level of an electron is it emits a photon. That's just how it goes. Anytime you accelerate an electron, it actually emits a photon, and decelerate, right? So what's happening here is electrons go in, and they emit their photon, and they continue on their merry way. Photon goes off. But the more electrons you pump into there, the more voltage you're going to need to actually get through that diode, right? So if you're cooking at 2.5 amps, then you're going to be at like 4.5 volts or more actually, apparently. But if I'm only at 1 amp forward current, then I only need 4 volts. That's great. Okay, that makes I get a lot more options now. All right, cool. That's good to know. All right, forward current versus normalized relative luminous flux. That's a lot of words I don't really understand. Normalized, okay. So that means it's been made to be equal to 1, which is probably why at 1 amp, which is the test. 1 amp I saw a couple times on here that was like the test current they used. That's why it's at 1, because it's been normalized. Showing you real data, or not the real data, but showing you the full scale data would probably make it for an ugly graph. That's almost certainly the reason. Relative. Okay, relative to what? Maybe these two are related and they just mean the same thing. Luminous flux. So the number of photons of light through a cross-sectional area. Amount of luminosity in a cross-sectional area. I don't know. It's been a long time since I've done optics. I'm just going to say is more brighter. Okay, so it's probably just giving you the brightness curve. So you see how the tangent right there, the tangent to the curve is a nice line right there. That probably tells you that's where you're going to get the most bang for your buck. Because after that is diminishing returns. You see how like the more you pump into it, the less you're going to get. You're gonna get more, right? But you're not going to get as much more as you would back here. Okay. So 1 amp is the sweet spot, is what it's trying to tell us. I wish sometimes they could just tell us. Forward current versus dominant wavelength. Okay, these are all pretty flat, and I don't care if the color is 100% true. Forward current versus the thing that I don't know about. I'll have to look that up later. I mean, it looks dire. It kind of drops down. That seems concerning, I guess. Okay, junction temperatures versus relative light output. I'm going to keep the junction temperature pretty much around 25°C. I'm not planning on cooking this thing. I mean, it's good to know, I guess. I mean, it does drop off like a son of a gun. As soon as you hit... Wow, as soon as you hit 37, red really takes a nosedive. Okay, good to know. But it's going to have... The application I'm going to have is going to have a lot of heat sinking on it, so I'm not concerned. All right, this looks good. I think we've found ourselves an LED. Now, next time I'm going to go through the LED driver, because now we've selected an LED, we've got to pump a constant current. Constant current means constant photons out, right? Because the photons that go in have a chance of emitting the electrons that go into it have a chance of emitting a photon. So, and that chance is pretty much linear. It's always the same, more or less. It's called the quantum efficiency of the semiconductor. So more electrons mean more photons, and that means we need a constant current if we want constant photons. So we're going to need a LED driver, which provides a constant current at the pretty high current that we're going to ask. This is an amp. We're going to be pumping some serious juice to this potentially. We'll see how that goes. All right, till next time. This has been the Alex Manassa. Feel free to hit the like the smash button, right? And subscribe for more videos. I'll see you guys later.